In this lesson, we're going to look at pseudo rate laws as they relate to integrated rate laws. Previously, we looked at the integrated rate laws for zero, first, and second order with respect to a single reactant. Let's say we have a reaction that has three reactants, A, B, and C. Here's the rate law. We can write a pseudo rate law with respect to the concentration of A if we make the concentrations of B and C significantly larger than the concentration of A. So then the concentration of A is the only concentration that will vary because B and C are so large. We can then combine together the concentration of B and C and the original rate constant into what we call a pseudo rate constant, K prime. And now we're focusing on the concentration of a single reactant, A, and we can talk about our integrated rate laws. Here's an example. It's number 58 from your end of chapter 12 problems. We've got three reactants, A, B, and C. And here's the rate law. Notice how C is missing. And so that must mean that it's zero order with respect to the concentration of C. And anything to the zero power is equal to 1. So in an experiment, we're looking at the concentration of A as a very small number compared to the concentration of B and C. So we're going to focus on the concentration of A and how it changes. So here's our rate law with respect to A. We have a pseudo rate constant times the concentration of A, and it is still first order with respect to A. And this pseudo rate constant will be equal to the original rate constant, and then the concentration of the other reactant there, B squared. So in A, we're going to calculate the value of, let's do the pseudo rate constant. And we get to use the integrated rate law for first order, since the reaction is first order with respect to A. Okay, so the natural log of the concentration of A equals negative KT plus the natural log of the initial concentration of A. And we can plug in what we know. Here's our initial concentration of A, that'll go here. And then at 8 seconds, that's our time, we know the concentration is here, so that will go right here. And then we can solve for our rate constant. Now this is actually going to be our pseudo rate constant with respect to A. If you solve, you get 0.12 inverse seconds, 1 over seconds, for our pseudo rate constant. Now for B, we can calculate the half-life for this experiment because we know the pseudo rate constant, and because it is first order with respect to A, we'll go ahead and we'll use our half-life equation for first order reactions. Okay, so our pseudo rate constant can go in here into our half-life equation and we can solve. We get a half-life of 5.8 seconds. So again, the concentrations of B and C were so much larger than the concentration of A that essentially they are going to be unchanged. And the only thing that will change in concentration is the concentration of A. So that's what we're basing our rate law on. That's what we're basing our half-life on. So now for part C, we're going to calculate the concentration of A after 13 seconds. So we want to solve for this right here. We know our time is going to be 13 seconds, and we know our pseudo rate constant from part A is 0.12, 1 over seconds. And from part A, we know still that the initial concentration was given right here. So we will plug that in and solve. And if we go through and solve, we get 2.1 times 10 to the negative third molar, since it is a concentration, or 0.0021 molar if you write it as an ordinary number. And then for part D, it asks for us to calculate the concentration of C after 13 seconds, which we certainly could do. However, this problem, we focused on the concentration of A, and we kept the concentration of B and C very, very large compared to the concentration of A, so that essentially they would remain unchanged. If you went through and you did the math, you would find after sig figs, that concentration is essentially unchanged. And so it would be 2 molar, the original concentration of C, after 13 seconds.